somewhere above us. The Milky Way is turning so slowly that its motion feels like stillness. The sun is racing around its hidden centre. Ancient stars are drifting through the halo. Dark matter is holding the whole spiral together, and behind black lanes of dust, new stars are quietly beginning to form. Our galaxy looks peaceful from Earth, but it is warped, layered, scarred by old collisions, and still growing in the dark. Thank you for spending part of your day, or night, here with this quiet journey through our cosmic home. If this kind of slow, thoughtful science helps you relax, please leave a like, subscribe for more calm space stories, and share this with someone who enjoys drifting into big questions. Also, tell me in the comments what time it is where you are, and where in the world you're listening from. Now, let the lights of the Milky Way open slowly around us. The Milky Way first appears not as a map, but as a pale, uneven river crossing the dark, a softened band of unresolved stars and hidden dust seen from a planet buried inside its own galaxy. From Earth, the galaxy does not reveal itself as the bright spiral familiar from diagrams. It presents only an inside view, a long cloudy arc where distance compresses into haze and structure becomes difficult to separate from light. The reason is simple and quietly limiting. The solar system sits within the Milky Way's disk, not above it. Every glance toward the galaxy is therefore a glance through the crowded plane itself, through layers of stars, cold gas, warm gas, dark clouds, glowing regions, and dust grains that catch and scatter visible light. A galaxy that might look graceful and organized from far away becomes, from within, a forest of overlapping trunks. The whole shape cannot be seen at once. It has to be inferred, piece by piece, from motions, distances, chemistry, radio signals, infrared glow, and the slow, patient work of surveys that turn scattered points into a three-dimensional structure. This is one of the first strange facts about the Milky Way. Humanity lives inside a galaxy so large that its basic form had to be discovered from within its own obscuring body. For a long time, the band of the Milky Way was not understood as the flattened disk of a vast stellar system. It was simply the luminous road of the night, a crowded brightness in the sky. Only later did measurements begin to show that the stars are not distributed evenly in every direction. They gather strongly along one plane, forming the flattened system that contains the Sun, Earth, and most of the visible stars in the galaxy. The pale band is not a surface, it is depth. It is the view along the grain of the galactic disk, where countless distant stars merge into a continuous glow because individual points of light become too faint and too numerous for the eye to resolve. Under a truly dark sky, the sight can feel rich and immense, but even that view is only a very small fraction of what exists. The unaided eye can see only a few thousand stars, while the Milky Way contains hundreds of billions. Most are too distant, too dim, too hidden, or too blended into the general radiance to appear as separate lights. This means the familiar night sky is not a full portrait of the galaxy. It is a narrow, visible surface of something mostly concealed. The hiddenness is not only a matter of distance, it is also a matter of material. The Milky Way is threaded with interstellar dust, made of tiny grains of carbon, silicate, ice, and other compounds. These grains are small, but in enormous numbers they become powerful filters. In visible light, they block and redden starlight, creating dark lanes that seem empty but are often full of cold material. Some of the darkest patches in the Milky Way are not holes in the star field. They are clouds lying in front of richer regions beyond. Behind them, star formation may be continuing, clusters may be forming, and young stars may be warming the gas around them. What looks like absence may be a veil. This distinction matters because it changes the way the galaxy has to be studied. Visible light alone gives an incomplete and sometimes misleading picture. It shows bright stars and glowing nebulae, but it fails where dust becomes thick. Infrared light passes through dust more easily and reveals hidden stars near the galactic centre. Radio waves trace cold hydrogen gas and molecular clouds across regions that optical telescopes cannot penetrate. X-rays and gamma rays reveal energetic processes near compact objects and hot gas. Each wavelength uncovers a different layer, as if the Milky Way is not one object but a set of overlapping realities, each visible only through a particular kind of listening. The galaxy's centre is a clear example of this limitation, in the direction of Sagittarius. The sky contains the crowded heart of the Milky Way, but visible light from the central regions is heavily obscured by dust in the disk. The human eye cannot simply look straight into the core and see what is there. Instead, astronomers reconstruct it from infrared observations, radio measurements, the orbits of stars, and the behaviour of gas. There, hidden behind the dust, lies a dense central region containing old stars, a bar-shaped structure, a bulge with complex geometry, and the supermassive black hole known as Sagittarius A star. From Earth, this centre is both near in galactic terms and deeply concealed in practical terms. It is part of the same home system as the Sun, yet it has to be approached through indirect evidence. The Milky Way is intimate and inaccessible at the same time. That tension runs through almost every attempt to understand it. The Sun itself does not sit near the centre. It orbits far out in the disk, in a quieter region between major spiral features, within a smaller structure often called the Orion Spur. This location shapes the view. Looking inward means peering through dense stretches of the disk toward the core. Looking outward means looking toward thinner regions, where the stars become less crowded and the outer galaxy fades into the halo. Looking along the plane produces the luminous band. Looking away from the plane opens into darker skies where far fewer Milky Way stars fill the line of sight. The sky therefore changes depending not only on what is out there, but on the angle through which the galaxy is being viewed. The Milky Way is not arranged for easy inspection. It surrounds the observer, hides behind itself, and turns perspective into part of the mystery. This is why the galaxy's structure had to be built from many kinds of clues. Star counts showed where stars are concentrated. Variable stars helped establish distances. Radio maps traced hydrogen through the obscuring dust. Infrared surveys revealed stars in hidden regions. The Gaia mission added extraordinary precision by measuring the positions and motions of huge numbers of stars, turning the galaxy from a static picture into a moving map. Motion is especially important because the Milky Way is not a fixed arrangement of lights. Every star is travelling, gas clouds orbit, clusters drift. The Sun moves around the centre. Even the spiral pattern itself is not a solid object. To understand the galaxy, it is not enough to ask where things are. It is necessary to ask how they move, where they came from, and what their paths imply about the mass that guides them. A still picture would miss the essential fact that the Milky Way is a system in motion, yet its motion is too slow for ordinary human perception. The stars appear steady across a lifetime, and the pale band of the Milky Way seems almost timeless. The change is real, but it unfolds across spans far beyond the scale of memory. The Sun takes hundreds of millions of years to complete one orbit around the centre. Spiral arms shift over long intervals. Clouds collapse into stars, but the process can take millions of years. Star clusters disperse gradually. Satellite galaxies are torn apart not in a single visible rupture, but in long gravitational unravelling. The galaxy is active, but its activity is quiet to eyes that live only briefly. It is a storm slowed down until it resembles stillness. This slow motion helps explain why the Milky Way can feel familiar and mysterious at once. It is the home of every night sky ever seen from Earth, yet its true form is a moving structure hundreds of thousands of light years across, embedded in an even larger halo of dark matter and ancient stars. The visible disk, bright as it seems, is only part of the system. Beyond it lies a diffuse halo where globular clusters, old stars, stellar streams, hot gas, and invisible mass extend the galaxy's reach far into space. The Milky Way is therefore not just the glowing band overhead, it is the bright disk, the obscuring dust, the hidden centre, the outer halo, the captured fragments of smaller galaxies, the dark matter that shapes rotation, and the faint outskirts where the boundary between galaxy and surrounding space becomes harder to define. Its edges are not sharp walls. They are fading zones of gravity, motion, and sparse matter. To call the Milky Way a spiral galaxy is accurate, but it is also incomplete. The word spiral suggests a clean pattern, something drawn from outside. The actual galaxy is warped, layered, dusty, barred, lopsided, and still assembling. It has swallowed smaller systems. It carries stars that did not form in its disk. It contains clouds that may become future stars and remnants of stars that died before the sun existed. It has a centre that is hidden, arms that are not fixed, a halo that outweighs the visible disk, and a history preserved not in a single record but in motion. Chemistry and scattered light. From inside, the first task is not to admire the whole shape, because the whole shape is not directly available. The first task is to accept that the view is partial. The pale river in the sky is a clue, not the answer. It is the nearest visible trace of a structure too large to stand outside, too dusty to see through completely, and too old to understand from a single moment. The Milky Way begins as a band of light, but the band is only the doorway. Beyond it lies a galaxy that has to be reconstructed from fragments. And those fragments already suggest that home is stranger, deeper, and less settled than its quiet appearance allows. The spiral arms of the Milky Way are often pictured as graceful lanes of stars curling outward from the centre, as if the galaxy were a wheel with luminous spokes that keep their form across time. That picture is useful from a distance, but it becomes less simple when the disk is understood from within. The arms are not permanent roads filled with the same stars forever. They are patterns of higher density, regions where gas, dust, and stars crowd together a little more than they do in the spaces between. The pattern moves through the galactic disk, and matter moves through the pattern. Stars enter an arm, spend part of their long orbit within it, and later drift away. Gas clouds pass into the denser region and are compressed. Some collapse into new stars, and for a time the arm shines more brightly with young blue stars and glowing clouds. What looks like a fixed structure is really a slow wave travelling through a rotating system, a form that persists while its ingredients keep changing. This is one of the Milky Way's quieter strange facts. The spiral shape is real, but it is not a solid thing. It is a rhythm, a crowding, a long gravitational pattern written in motion. The difficulty begins with the fact that the Milky Way cannot be seen from outside. In other spiral galaxies, arms can be traced by their young stars, dust lanes, and hydrogen clouds. In our own galaxy, the same features have to be mapped from the inside, where dust hides distant regions and distance estimates can be uncertain. Astronomers have used radio emission from hydrogen, infrared light from star-forming regions, and the positions of bright young stars to build a picture of the arms. Even then, the result is not as neat as a textbook diagram. Some maps show several major arms, Some emphasize stronger arms with branching segments. Others reveal spurs, feathers, gaps, and fragments. The Milky Way is not a clean pinwheel. It is a layered spiral with uneven features, some long and continuous, others broken or fading, all shaped by the shared motion of matter in the disk, from Earth. This uncertainty is not a failure of observation alone. It comes from living inside the structure being measured. A star cloud that looks nearby may lie along the same line of sight as a more distant arm. Dust may remove an entire region from visible view. Gas can trace a feature that older stars do not follow as clearly. The apparent simplicity of the spiral becomes more complex as more kinds of data are added. The arms are not merely bright curves. They are places where gravity, orbital motion, and interstellar material interact. The term density wave helps describe this behaviour. It means that the arm is a wave of crowding moving through the disk, somewhat like a traffic slowdown that travels along a road while individual cars enter and leave it. In the same way, the stars are not permanently attached to the arm. They pass through a region where the arrangement of orbits produces a higher concentration of matter. The comparison is imperfect, because galaxies are shaped by gravity rather than roads, but it captures the essential distinction. The visible arm is a pattern, not a chain of fixed objects. This matters because it explains why spiral arms are bright. The brightness does not come simply from having more old stars. It comes strongly from the birth of new stars. Cold gas enters the denser region. Pressure rises, and clouds that were once barely stable can begin to collapse. Massive young stars form quickly, burn hot, and shine blue-white against the surrounding dust. Their ultraviolet light excites nearby gas, causing nebulae to glow. Because these massive stars live briefly by cosmic standards, they tend not to travel far before they die. They mark the arms like fresh sparks along a slow current. Older, cooler stars spread more evenly through the disk and do not outline the spiral so sharply. The arms therefore show both structure and timing. They are not just where matter is. They are where recent star formation has made the pattern visible. The Sun does not sit in one of the Milky Way's largest arms. It lies in a smaller feature called the Orion Spur, sometimes described as the Orion Arm or Local Arm, a minor segment between larger structures such as the Sagittarius Arm and the Perseus Arm. This location is easy to overlook because the word minor can make the region sound insignificant. Yet the Orion Spur is the immediate galactic neighbourhood of Earth, the lane of stars and gas that contains the solar system, nearby star-forming regions, and many of the familiar bright stars seen from the night side of the planet. It is not empty space between true arms. It is a real structure, a smaller bridge or spur in the larger spiral pattern. The Sun's home is therefore not at the centre of a grand arm, nor in a complete void between arms, but in an intermediate place, a quieter side channel within the larger flow of the galaxy. That position may matter. Major spiral arms tend to contain denser gas, more active star formation, and more massive young stars. Massive stars can end their lives as supernovae, spreading heavy elements, but also releasing intense radiation and shock waves. A region with fewer such events may offer a more stable environment over long spans of planetary time. This does not mean the Orion Spur was selected for life, or that its relative quietness is the only reason Earth remained habitable. The history of life depends on many factors, from the Sun's stability to Earth's atmosphere, magnetic field, oceans, impacts, and internal geology. Still, the galactic setting is part of the background. A solar system does not evolve in isolation from the galaxy. It moves through varying stellar neighbourhoods, changing gas densities and shifting spiral patterns. The quietness of the local spur may be one condition among many that made long biological continuity less difficult. The Sun's path through this pattern is not a simple circle painted onto a fixed spiral. It orbits the galactic centre while the spiral pattern has its own speed. In some regions, stars overtake spiral arms. In others, the pattern may move differently relative to the stars, near a special distance called the corrotation radius. The average orbital speed of stars more closely matches the speed of the spiral pattern. The Sun is often discussed as being near this kind of boundary, though the exact details remain debated. If the solar system's motion keeps it from crossing major spiral arms too often, that could reduce encounters with dense star-forming regions and the hazards associated with them. The idea is subtle, and it should not be treated as settled proof. Its importance lies in what it suggests. Even the habitability of a planet may depend partly on a slow choreography between a star and the spiral structure around it. The Milky Way's arms also change with time. They can be stretched by the central bar, disturbed by satellite galaxies, stirred by giant molecular clouds, and modified by the galaxy's own uneven rotation. The bar at the centre helps organise material in the inner disk and can feed spiral patterns outward. Passing dwarf galaxies may tug at the outer regions and help create warps, ripples, or asymmetries. Supernovae and stellar winds carve bubbles in the gas, while magnetic fields guide charged particles and dust in ways that complicate the flow. The spiral pattern is therefore not a simple decorative feature imposed on the galaxy. Its shape records both internal dynamics and outside disturbances. Every curve is part of a larger negotiation between gravity, gas, rotation, and time. From inside the Orion spur, the spiral arms reveal themselves indirectly. The Milky Way band shows denser regions along the galactic plane, but it does not label the arms clearly. Nearby nebulae and star clusters belong to the local structure. Farther away, radio maps trace hydrogen into long segments. Infrared surveys find young stars hidden behind dust. Measurements of stellar motion help distinguish one feature from another. The result is a galaxy that becomes more detailed as observation improves, but not necessarily simpler. Better maps have shown that home is not a perfectly ordered spiral, but a moving, branching arrangement. The arms may split, merge, fade, or bend. The Orion spur itself may be longer and more important than once assumed. The more precisely the Milky Way is measured, the less it resembles a flat symbol, and the more it becomes a physical place with irregularities, currents, and local histories. The strange beauty of the spiral arms is that they appear stable only because human lives are short. Across one night, they're invisible as structures. Across one lifetime, nearby stars barely shift. Across millions of years, clouds form stars, bright stars die, clusters drift apart, and the solar system continues its long path through the disk. The galaxy is not a clockwork drawing. It is a slow river of orbits, with waves of density passing through it, and brief generations of massive stars lighting the crests. The arms give the Milky Way its recognizable shape, but they do so without standing still. They are form without permanence, structure without rigidity, and their motion makes the next fact more difficult to feel. The Sun itself is not resting inside this pattern, but travelling through it on an orbit whose scale turns time almost silent. The Sun's orbit around the Milky Way is fast enough to seem impossible in ordinary terms, yet slow enough that its motion disappears inside daily life. Earth turns beneath the sky, the Moon follows Earth, and the planets trace their paths around the Sun. But the whole solar system is also moving through the galaxy, swept along with the disk at a speed of roughly 828,000 kilometers per hour. That number sounds enormous, and it is. In every second, the Sun carries Earth across more than 200 kilometers of galactic space. Nothing in ordinary experience provides a useful comparison for such motion. Still, The scale of the Milky Way is so much larger that this speed barely advances the solar system along its full path. A single orbit around the galactic centre takes about 225 to 250 million Earth years. This long circuit is often called a galactic year, though the phrase almost hides the depth of what it means. One galactic year is long enough for continents to rearrange, oceans to open and close, climates to shift, and entire branches of life to rise, flourish, and vanish. The sun is racing, but the road is so vast that its journey feels almost still. This is one of the strange facts that makes the Milky Way difficult to hold. In the mind, speed and slowness are not opposites at galactic scale. They exist together, folded into the same orbit. The solar system lies far from the galaxy's crowded centre, in the broad disk where the rotation is guided by the combined gravity of stars, gas, dark matter, and the mass hidden deeper within the Milky Way. The path is not a perfect circle drawn on a flat sheet. It is an orbit through a living gravitational field, influenced by the uneven distribution of matter, the spiral pattern, the central bar, nearby stars, giant clouds, and the invisible halo that surrounds the galaxy. Even so, the average motion is coherent enough to picture the sun travelling around the centre, carrying planets, moons, asteroids, comets, dust, spacecraft, oceans, forests, cities, and all living memory with it. The solar system has completed only a small number of these galactic circuits since its formation. The Sun is about 4.6 billion years old, and over that time it has made fewer than 25 orbits around the Milky Way. In human language, the Sun feels ancient. In galactic language, it has gone around the centre only a few dozen times at most. This changes the meaning of age. The solar system is old enough for rocks to carry deep histories and for life to have transformed a planet. Yet it is still a relatively modest traveller within the wider city of stars. The idea of a galactic year creates a different kind of calendar, one in which familiar eras of Earth history occupy positions along an orbital arc, when the first dinosaurs appear. The solar system is not in exactly the same region of the galaxy it occupies now. When the earliest mammals move through Mesozoic forests, the sun is elsewhere along the Great Curve, when flowering plants spread, when mountains rise and erode, when ice ages come and go. The solar system continues its passage through changing stellar neighbourhoods. The surrounding stars are not permanent neighbours. Many that drift near the sun today were not nearby in the deep past and will not remain near in the far future. Close encounters happen on wide timescales, usually gentle and distant, but enough to alter the outer edges of the solar system or disturb distant comets over long periods. Home, in this sense, is not a fixed address inside the Milky Way. It is a moving region, a temporary arrangement of nearby stars within a larger flow. The night sky therefore has a history. Its constellations are not eternal designs. They are momentary projections created by the current positions of stars that are themselves orbiting, drifting, and migrating. Across hundreds of thousands of years, familiar patterns deform. Across millions, they dissolve into entirely new arrangements. Across a galactic year, the sky belongs to a different neighbourhood altogether. The sun's movement is not limited to its long path around the centre. It also rises and falls through the galactic plane in a slow, vertical oscillation. The Milky Way's disk is flattened, and the sun travels near its mid-plane, but it does not remain exactly there. As it moves around the galaxy, it passes slightly above and below the dense central layer of the disk, pulled back by the gravity of stars and gas concentrated near the plane. The movement is gentle and immense, sometimes compared to a cork drifting over a very slow swell, but the mechanism is not water. It is gravity acting across the thickness of the galactic disk. Over tens of millions of years, the solar system completes these upward and downward motions, crossing the plane and then climbing again. This adds another rhythm to the journey, not merely around the galaxy, but through its layered body. Some researchers have wondered whether this vertical motion could affect Earth by bringing the solar system through denser regions of interstellar material, or altering the rate at which comets are disturbed in the distant Oort cloud. The idea has been explored in connection with possible extinction cycles, but the evidence remains uncertain and debated. The careful conclusion is not that the Sun's bobbing motion controls life on Earth, but that Earth's history may have galactic background conditions. The solar system is sheltered by the Sun and shaped by planetary processes, yet it is not sealed away from the Milky Way. It moves through a changing environment. The density of nearby stars shifts. The interstellar medium varies. Spiral structure is crossed or avoided depending on orbital position. Cosmic rays, dust, and gravitational perturbations form part of the broader setting in which a planet's long story unfolds. The link is subtle and often indirect, but it widens the frame. Earth is not simply orbiting a star. It is travelling with that star through a galaxy that has its own weather, geography, and time. The galactic year also reveals how difficult it is to speak of return. After one orbit, the Sun may be back to a similar position around the centre, but the galaxy itself has changed. Spiral patterns have shifted. Gas clouds have collapsed or dispersed. Massive stars that once marked an arm have died. New clusters have appeared. Dwarf galaxies have continued their slow unravelling in the halo. The central bar has turned. Nearby stars have moved along their own paths. A galactic year is therefore not a simple loop back to the same place. It is more like a spiral through time, where the Sun completes a circuit in a system that has not remained the same during the circuit. The last time the solar system occupied roughly this part of its orbit, Earth was not a familiar world with modern coastlines and familiar life. The continents were arranged differently, and the biosphere belonged to another chapter. The next time the Sun returns to a comparable galactic longitude, Earth will again be changed in ways that cannot be known with certainty. The orbit repeats, but the conditions do not. Even the Sun's speed is part of a larger mystery. In a simple solar system, planets farther from the central mass tend to orbit more slowly in a clear pattern. Galaxies do not follow that expectation in the same way. Stars in the outer regions of the Milky Way move faster than the visible matter alone can explain, which is one of the major lines of evidence for dark matter. The Sun's orbit therefore takes place inside an unseen gravitational architecture. Its path is not determined only by the stars that shine, or by gas that glows, or by the bright centre hidden behind dust. It is shaped by a vast dark halo whose substance remains unidentified. The familiar yearly orbit of Earth around the Sun can be calculated from visible bodies. The galactic orbit of the Sun requires acceptance that most of the galaxy's mass is not visible at all. The solar system moves inside a structure whose greatest weight cannot yet be seen. There is a quiet humility in that motion. The Sun is not fixed in a cosmic centre. It is not stationary while the galaxy turns around it. It is one star among hundreds of billions, moving through a minor spur, circling a hidden core, swaying through the plane, and carrying a small planetary system through one long segment of a much older rotation. The apparent stillness of the night sky is a local illusion created by distance and short lifetimes. Beneath it, every star has a path. Every path belongs to the galaxy's mass. Every orbit records the shape of forces both visible and invisible. The solar system's journey around the Milky Way is not dramatic in any sudden sense. It is too slow for spectacle. Its power comes from scale. It turns the history of Earth into a brief passage along a stellar orbit and turns the galaxy into the larger clock in which that history has unfolded. The Sun is moving quickly, but the Milky Way is wider than speed can easily conquer, and that is why the galactic year feels less like a measurement than a reminder the motion of home is vast, continuous, and almost perfectly hidden by its own calm. A diagram of the Milky Way usually looks clean because diagrams have to make choices. They show a flat spiral, a bright centre, and curving arms arranged with a symmetry that helps the mind understand the whole at once. The actual galaxy is less obedient. Its disk is not a single thin plate. Its centre is not a simple round concentration of stars. Its outer regions do not lie perfectly flat. Even its apparent balance from side to side breaks under closer measurement. The Milky Way is a layered structure shaped by motion, age, gravity, and old disturbances that have not fully faded. From inside it, the difference between a simple picture and the living system can be easy to miss, because no one sees the galaxy laid out below like a map. Yet the clues are there in star motions, chemical ages, infrared surveys, radio maps of gas, and the way distant stars sit above and below the main plane. The Milky Way is not merely a spiral. It is a thickened, warped, barred, uneven body whose shape records its history. The first layer is the thin disk, the broad flattened region where the Sun travels and where much of the galaxy's gas, dust, and young stars are found. It is called thin only in comparison with the larger scale of the galaxy. Across its full breadth it stretches for tens of thousands of light years, but vertically it is much narrower than it is wide, like a luminous layer pressed into a great rotating sheet. This is where many familiar features belong: molecular clouds, open star clusters, bright blue young stars, nebulae, and the dust lanes that darken parts of the Milky Way band. The thin disk is active because it still contains the cold material needed for star formation. It is the galaxy's more youthful layer, though not everything in it is young. Stars of many ages move there, including the Sun, but the presence of gas makes it a continuing workshop rather than only an archive. Above and below this thin layer lies the thick disk, older, puffier, and less sharply confined. Its stars tend to be more ancient and poorer in heavy elements than many stars in the thin disk. They move on orbits that carry them farther from the central plane, giving the disk a greater vertical depth. The thick disk may preserve the memory of an earlier Milky Way, perhaps stirred by mergers, internal heating, and the rough assembly of the young galaxy. Its stars do not form a separate object in the way a moon separates from a planet. They are part of the same galactic system, but their motions and chemistry reveal that they belong to a different chapter. The thin disk carries much of the galaxy's ongoing star formation. The thick disk carries a record of older conditions, when the Milky Way had not yet settled into its present shape. The two layers overlap, and that overlap is part of the difficulty. The galaxy is not built like stacked shelves. It is more like sediment in motion, with older and younger populations mixed but still distinguishable by careful measurement. Near the centre, the shape becomes even less like the simple spiral seen in diagrams. The Milky Way is a barred spiral galaxy. Instead of a perfectly round central hub, it contains a long bar of stars crossing the inner region. This bar rotates, and its gravity helps organise gas and stars in the central parts of the disk. Bars are common in spiral galaxies, but their presence changes the meaning of the centre. The inner Milky Way is not merely a place where orbits become tighter. It is a region where elongated stellar paths support a rotating structure, where gas can be funneled inward, and where the geometry of the whole disk is shaped by the bar's pull. The bar connects the disk to the bulge and helps influence where spiral arms begin or bend. It is not just an ornament inside the galaxy, it is a gravitational engine slowly stirring the inner system. Around and through this bar lies the bulge, and even that word can mislead. A bulge sounds smooth and round, but observations show that the central bulge of the Milky Way has a boxy, peanut-like form when viewed in certain ways. This shape likely grew from the bar itself. Over time, the bar can become unstable in the vertical direction, buckling and puffing upward and downward from the plane. The result is a central region that swells into a three-dimensional structure, more like a thickened hourglass or a peanut than a simple sphere. The stars there are crowded and old, and their paths carry the imprint of the galaxy's internal dynamics. This is one of the quiet surprises of modern mapping. The Milky Way's heart is not just hidden by dust, it is geometrically strange. The centre is layered, elongated, and buckled, a structure formed not by a single event, but by billions of years of stellar orbits settling into patterns. Farther out, the disk itself refuses to remain flat. Radio observations of hydrogen gas reveal that the outer Milky Way bends upward on one side and downward on the other. This warp is not obvious from ordinary starlight, because the sun sits within the disk and the effect is spread across enormous distances. But when the gas is mapped, the shape becomes clear. The galaxy's outskirts curve like a spinning sheet that has been gently twisted. The cause is still studied. The pull of satellite galaxies may contribute, especially the Magellanic Clouds as they move through the Milky Way's halo. The dark matter halo may also play a role if its shape or motion is not perfectly aligned with the disk. Internal waves and past encounters could add further distortion. The warp shows that the disk is not a rigid object. It responds to tugs, flows, and imbalances, bending across time rather than holding a perfect plane. The wobble of the outer disk connects to a broader truth: the Milky Way is not symmetrical. One side can appear thicker or more disturbed than another. Spiral arms differ in brightness and reach. The outer disk is lopsided. Star counts in different directions do not always balance neatly. The halo itself contains streams and uneven structures left by absorbed galaxies. These irregularities are not flaws in an otherwise perfect form. They are records. A galaxy that grows by drawing in gas, stirring itself with bars, forming stars in uneven clouds, and absorbing smaller companions should not be expected to remain immaculate. Its shape is a memory of interactions. A satellite galaxy passes, and the disk may ripple. A merger adds stars on tilted orbits. Gas falls in at an angle, and the outskirts bend. The Milky Way's beauty is not the beauty of perfect design, but of accumulated motion that has not erased its own disturbances. Even the division between inner and outer structure is not sharp. The bar influences the central regions. Spiral arms carry star formation outward. The thin disk fades gradually with height. The thick disk blends into the lower halo. The warp becomes more prominent in the outskirts. The halo surrounds everything, faint in stars but massive in unseen matter. Each component has its own history, but none is completely independent. The galaxy is one gravitational system, and every part feels the presence of the rest. Stars in the thick disk reveal an older dynamical state. Gas in the thin disk responds to spiral patterns and the central bar. The bulge records the buckling of the inner bar. The warp may respond to satellites and dark matter. The lopsidedness hints at encounters that continue to leave their signatures. Shape in the Milky Way is not only appearance, it is evidence. This is why the familiar flat spiral image should be treated as a beginning rather than a conclusion. It captures the broad truth that the Milky Way is a rotating disk with spiral structure, but it leaves out the depth, age layering, inner bar, peanut bulge, warp, and a symmetry that make the galaxy physically real. The more carefully it is mapped, the more it resembles a place shaped by long weather rather than a clean astronomical emblem. Its layers speak in different languages, young stars in bright clusters, old stars in heated orbits, gas bent through the outskirts, dust thickening the plain, and central stars locked into an elongated rhythm. To live inside such a galaxy is to inhabit a structure that seems calm only because its changes unfold slowly. The Milky Way holds its shape, but not perfectly. It turns, thickens, bends, ripples, and remembers. Beneath the soft band of light in the sky is a layered galactic body, and the next hidden layer is colder and darker still, where the raw material of future stars waits behind the dust. Inside the dark lanes of the Milky Way, some of the most important regions are almost defined by what visible light cannot do. A molecular cloud may cover a rich background of stars so completely that it looks like a tear in the sky, a black shape against the pale band of the galaxy. Yet the darkness is not emptiness. It is cold gas and dust, gathered across light years into a dense interstellar structure where matter can become quiet enough, shielded enough, and heavy enough to begin collapsing under its own gravity. These clouds are called molecular because much of their hydrogen has paired into molecules, a form that survives only where starlight is softened by dust and where temperatures fall low enough for fragile bonds to remain. They are among the coldest large structures in the galaxy, only a little warmer than absolute zero in their deepest interiors, and they are the raw reservoirs from which new stars and planetary systems are made. The strange fact is that the Milky Way's brightest future often begins in its least transparent places. A dark patch in the galactic band may be a nursery, not a void. The process is slow and uneven. A giant molecular cloud can stretch across many tens or even hundreds of light years, but it does not collapse all at once. Turbulence runs through it. Magnetic fields thread it. Older stars nearby may heat one edge while another remains cold and dense. Within the larger cloud, smaller clumps and filaments form, and within those clumps, gravity begins to find the places where it can win. A region becomes slightly denser than its surroundings. It pulls in more material. Its center cools efficiently because dust and molecules carry energy away. If the inward pull continues, the gas gathers into a core that contracts, spins, and flattens. At the heart of the core, pressure rises. A protostar begins as a buried object, not yet a stable star but already warming the material around it. The visible galaxy may show only a dark cloud from outside, while inside it the earliest architecture of a star system is being assembled. Dust is central to this hidden beginning. It is easy to think of dust as something that merely blocks the view, but in the Milky Way it also shapes the physics of birth. Dust grains shield molecules from harsh radiation, allowing cold chemistry to persist. They help gas lose heat, and cooling is essential because warm gas resists collapse. They provide surfaces on which atoms can meet and form molecules, including molecular hydrogen and more complex compounds. They absorb ultraviolet light from young stars and re-emit energy in infrared wavelengths, turning invisible darkness into a glow that telescopes can detect. Dust hides the nursery in one kind of light and reveals it in another. This is why infrared astronomy changed the view of the galaxy so deeply. Regions that appeared opaque in visible light became crowded with newborn stars when observed at longer wavelengths. What had looked like a curtain became a window, but only after science learned to look with different eyes. Radio observations reveal another layer. Cold hydrogen emits radio waves that can be traced through dust, outlining the large-scale structure of the Milky Way. Molecules such as carbon monoxide act as tracers for molecular hydrogen, which is otherwise difficult to observe directly in the coldest clouds. By following these signals, astronomers map giant cloud complexes, spiral arms, and star-forming regions hidden across the disk. The galaxy is therefore not mapped only by stars. It is mapped by gas that has not yet become stars, by the reservoirs that hold future light in unlit form. These radio maps show that the interstellar medium is not smooth. It is filamented, clumped, stirred, and layered, with bubbles carved by old supernova and dense ridges where new collapse may begin. Between the stars is a restless geography, and molecular clouds are its shadowed highlands, places where matter gathers until gravity can make something lasting. The spiral arms help organize many of these nurseries, though they do not hold them permanently. As gas flows through a denser arm pattern, it can be compressed, making collapse more likely in clouds already near the threshold. This is one reason spiral arms glow with young stars and nebulae. The arms are not simply decorations of starlight. They are regions where the conditions for star formation are repeatedly renewed. Massive young stars then change their surroundings almost immediately. Their radiation heats gas. Their stellar winds push material outward. Their eventual supernovae send shock waves through nearby clouds. A nursery can therefore be both creative and destructive. It gathers matter into stars. But the first massive stars born within it may disperse the remaining gas before smaller stars finish forming. Star birth is not a peaceful conversion of cloud into light. It is a negotiation between collapse and disruption, between gravity drawing inward and young stars forcing their birthplace apart. Some of the Milky Way's most famous nebulae belong to this cycle. The Orion region, close by in galactic terms, is part of a larger molecular cloud complex where bright young stars illuminate gas while deeper regions remain dark and cold. In more distant parts of the disk, enormous star-forming complexes are hidden behind dust and known mainly through infrared and radio light. These regions contain embedded clusters, protostars, outflows, disks, and dense cores still waiting to ignite. A protostar often throws narrow jets from its poles as material falls onto it through a rotating disk. That disk is not an accidental detail. It is the leftover structure from which planets may form. Around young stars, grains collide and stick, pebbles grow, planetesimals gather, and worlds begin as a secondary consequence of star formation. In the Milky Way, the making of stars and the making of planetary systems are not separate stories. They arise from the same cold clouds, the same dust, and the same conservation of angular momentum that turns collapse into rotation. The chemistry of these clouds gives the process a deeper significance. Interstellar clouds contain water ice, carbon-bearing molecules, alcohols, simple organics, and larger compounds built around rings of carbon. None of this is life, but it is chemically rich material that can be inherited by forming planetary systems. Comets, asteroids, and young planets may receive ingredients that were assembled before the star itself fully settled. The Milky Way is therefore not only a machine for making light, it is a chemical environment where complex matter circulates through cold clouds, dying stars, newborn disks, and small bodies that may later fall onto planets. The atoms and molecules that enter a nursery carry earlier histories. Some were forged inside older stars, some were released by supernovae or gentle stellar winds, some formed on dust grains in the cold. By the time a star is born, it is already part of a long inheritance. Not every cloud succeeds in becoming a nursery. Some remain starless for long stretches, rich in molecular gas but held back by turbulence, magnetic support, low density, or disruptive external forces. These dark clouds are important because they show that gravity does not act alone. A cloud may have the raw material for stars and still wait in a suspended state, needing compression from a spiral arm, the shock wave of a supernova, the pressure of nearby radiation, or the slow dissipation of internal turbulence before collapse can begin. The galaxy contains many such possibilities, reservoirs of futures that may or may not be realized. This makes star formation less like a simple rule and more like a threshold. Matter gathers, cools, and waits. Sometimes it crosses the boundary into ignition, and sometimes it is dispersed before the boundary is reached. The Milky Way's rate of star formation has changed over time. In its younger history, the galaxy likely formed stars more rapidly, when gas was more abundant and conditions were more unsettled. Today it still forms stars, but at a calmer pace. The nurseries have not vanished. They have become part of a mature spiral system whose activity is steady rather than explosive. This quieter phase is still rich with consequence. Every new star slightly changes the galaxy's future population. Every planet forming in a disk adds another possible world. Every massive young star prepares the material for later generations by eventually enriching the surrounding medium. In the shadows of molecular clouds, the Milky Way continues to transform old matter into new structure. The darkness along the galactic band is therefore not the opposite of creation. It is one of creation's conditions. Behind the dust, gravity searches for dense centres, chemistry deepens in cold interiors, and unborn systems take shape before visible light announces them. The galaxy's nurseries are hidden because the same material that makes stars possible also conceals their beginning, and that concealment gives the Milky Way one of its gentlest reversals. The places that look least luminous may be where the next light is already forming. A star does not leave the Milky Way unchanged when its life ends. Long before any explosion, it has already altered the space around it, drawing gas from an old cloud, burning that material into heavier elements, sending winds outward, and shaping the surrounding interstellar medium with heat and radiation. But for massive stars, the final act is far more forceful. When the core can no longer support itself, collapse becomes unavoidable, and the outer layers are driven outward in a supernova. For a brief time, one dying star can release enough light to rival the brightness of a galaxy, but the visible flash is only the beginning of its meaning. The shock wave expands into surrounding gas. Newly forged elements are thrown into space. Nearby clouds are compressed, stirred, heated, or torn apart. The death of one star becomes a change in the conditions from which other stars may later form. This is one of the Milky Way's deepest cycles. Matter does not simply appear in stars and vanish with them. It circulates, it is burned, scattered, cooled, gathered, and used again, so that the galaxy becomes not a fixed collection of lights, but a long system of renewal. The clouds described as stellar nurseries are therefore not untouched reservoirs. They are inherited material, enriched by earlier generations, carrying the chemical memory of stars that lived and died before the sun was born. In the earliest universe, ordinary matter was mostly hydrogen and helium, with only tiny traces of other light elements. The heavier atoms needed for rocky planets, oceans, atmospheres, and bodies had to be made later. Stars performed much of that work. In their cores, nuclear fusion built elements such as carbon, oxygen, neon, magnesium, silicon, and sulfur across different stages of stellar life. In the most massive stars, fusion continued until iron and related elements accumulated near the centre, a point where further fusion no longer provided the energy needed to hold the core up against gravity. When support failed, the collapse was sudden and extreme. The rebounding shock, aided by complex physics involving neutrinos and turbulent flows, drove the outer layers outward. In that moment, the star became both an ending and a delivery system, returning processed material to the galaxy around it. The word explosion can make a supernova sound like a single violent point. But in the Milky Way, its influence spreads through space and time. The expanding remnant becomes a shell of hot gas moving through the interstellar medium. At first, it races outward, carrying enormous energy. Later, it slows as it sweeps up surrounding material. The shock front can heat gas, ionize atoms, accelerate particles, and shape magnetic fields. In some places, it carves a cavity, leaving a bubble of rarefied hot plasma. In other places, it pushes against colder clouds, squeezing them into denser forms. Whether that compression leads to new star formation depends on the cloud's condition. A stable cloud may be disrupted instead of helped. A cloud already near collapse may be tipped across the threshold. Supernovae are not simple creators or simple destroyers. Their role depends on timing, distance, density, and the structure of the material they encounter. That complexity makes them central to the galaxy's ecology. The interstellar medium between stars is thin by earthly standards, but it is not uniform. It contains cold molecular clouds, warmer atomic gas, ionized regions, dust grains, magnetic fields, cosmic rays, and hot bubbles left by old explosions. Supernova help keep that medium turbulent. Their shocks stir gas across many scales, breaking smooth clouds into filaments and pushing material into shells. When many massive stars form together in a cluster, their winds and later supernova can combine, creating superbubbles that grow until they break out of the disk. Hot gas can then rise into the halo through chimney-like channels, carrying energy and heavy elements away from the crowded plane. Over millions of years, some of that gas cools and falls back, joining the disk again in a cycle often called the galactic fountain. The Milky Way breathes through heating and cooling, outflow and return, pressure and collapse. This circulation is one reason the chemical composition of the galaxy changes across time. Each stellar generation forms from gas that has been altered by earlier generations. The first stars were nearly metal-free in the astronomical sense, meaning they contained almost no elements heavier than helium. Later stars formed from gas enriched by supernovae and stellar winds. The Sun belongs to this later history. Its existence depends on earlier stars that made and scattered the elements now found in the solar system. The calcium in rocks, the oxygen in water, the iron in Earth's core, and the carbon that allows complex chemistry all trace back to stellar processes before the Sun. The Milky Way is therefore chemically cumulative. It remembers its past in abundance patterns. Some old halo stars remain metal-poor because they formed before much enrichment occurred, or because they came from smaller systems with slower chemical histories. The galaxy's chemistry is not evenly mixed paint. It is a layered record of birth, death, circulation, and merger. Supernovae also create messengers that keep travelling after the flash fades. Their shock waves can accelerate charged particles to nearly the speed of light, producing cosmic rays that move through the Milky Way, guided and scattered by magnetic fields. Their remnants can shine in radio, optical, and high-energy wavelengths, depending on temperature, particles, and surrounding gas. A remnant may appear as a delicate shell or tangled filament, but beneath the shape lies a physical transition. A star has returned energy to the medium and changed the pressure, magnetism, and composition of part of the disk. Over time, the visible structure disperses, the atoms remain, they mix into clouds, freeze onto grains, become part of new cores, and perhaps enter planets. A supernova remnant is temporary, its material future is not. Not all recycling comes from massive explosions. Lower mass stars, including stars more like the Sun, shed their outer layers more gently near the ends of their lives. They swell into red giants, lose material through winds, and may leave behind glowing shells known as planetary nebulae. while the exposed core becomes a white dwarf. These quieter deaths return carbon, nitrogen, and dust to the interstellar medium. They do not stir the galaxy with the same force as supernovae, but they enrich it patiently. Together, explosive and gentle endings create a broader cycle. Massive stars act quickly, living briefly and returning energy after only a short time by cosmic standards. Smaller stars live longer, releasing material after billions of years. The galaxy receives matter on many clocks at once, some in sudden shock fronts, some in slow winds, and some only after long delay. The recycling cycle is not perfectly efficient. Some gas is heated until it resists collapse. Some heavy elements become locked in long-lived stars, planets, asteroids, or stellar remnants. Fresh gas can also fall in from outside the galaxy, diluting enriched material and sustaining star formation. The Milky Way is not a closed box. It gains, loses, mixes, and transforms matter across enormous spans of time. New stars form from gas that is neither pristine nor fully spent. In every newborn system, there is a hidden ancestry of collapse, fusion, explosion, cooling, and reassembly. The calm appearance of the Milky Way can hide how much of its beauty comes from interruption, without stellar death. The galaxy would be chemically poor, lacking much of the material needed for rocky worlds. Without shock waves, some clouds might remain suspended longer, waiting for a trigger that never comes. Without winds and explosions, the interstellar medium would be less stirred, less structured, less able to exchange material between regions. Yet too much violence can also prevent birth, dispersing clouds before they collapse, or bathing young systems in harsh radiation. The galaxy depends on balance rather than peace. Creation and destruction are not cleanly separated. A star that dies may erase its immediate surroundings and still prepare distant beginnings. A cloud compressed by an old shock may form stars that later repeat the cycle. The Milky Way renews itself through events that would seem final if seen only up close. This gives the galaxy's light a layered meaning. Every star shining in the disk is not merely a point of fusion, it is part of a lineage. Some of its atoms were born in the early universe, others were forged in older stars, some may have crossed the disk in a hot bubble, cooled in a halo flow, settled into a molecular cloud, and joined a rotating core. The Sun is no exception. It formed from enriched material, which means the solar system carries the residue of earlier stellar lives. The planets are assembled from recycled galactic matter. Earth is not separate from that cycle, but one of its quiet outcomes. The next stars forming behind the dust will inherit material from stars dying now, just as the Sun inherited the work of stars that vanished before it formed. The Milky Way is therefore not only a place where stars are born and die, it is a system in which death becomes distribution. Distribution becomes cloud, cloud becomes star, and star becomes memory. In that cycle, the ancient past is not gone. It is diluted, transformed, and still shining in new forms. Leading outward toward the older stars that preserve the earliest chapters of the galaxy, almost unchanged. The halo of the Milky Way begins where the bright disk loses its authority. It is not a sharp boundary, not a shell that can be crossed like a surface, but a wide, thinning volume of old stars, globular clusters, streams, remnants, hot gas, and dark matter extending far beyond the familiar spiral pattern. In the disk, the galaxy feels structured by lanes, clouds, arms, and new stellar birth. In the halo, the order is stranger and more ancient. Stars move on tilted, elongated paths that carry them above and below the plane. Some travel in directions that do not follow the main rotation of the disk. Many are faint, sparse, and chemically old, belonging to populations that formed before the Milky Way settled into its present shape. or were brought in from smaller systems that the galaxy absorbed. The halo is therefore not simply the outskirts, it is an archive, a dim surrounding memory of the galaxy's earliest assembly, where the first chapters survive because they were never fully mixed into the bright rotating plane. The stars of the halo often differ from the Sun in one revealing way. They tend to be metal poor. In astronomy, metals means elements heavier than hydrogen and helium. Not only the metals familiar from everyday language, a metal-poor star contains fewer of these heavier elements, and that matters because heavy elements are built gradually by earlier generations of stars. The first gas in the universe did not contain iron, calcium, oxygen, or carbon in the amounts later galaxies would know. Those elements had to be forged inside stars and scattered by stellar deaths. A star with very little heavy material is likely to be old, born from gas not yet enriched by many previous stellar generations. It can act as a chemical fossil. Its surface preserves the composition of the cloud from which it formed, and that composition carries information from a time when the Milky Way itself was still incomplete. The oldest halo stars are not old merely because they have survived a long time. They are old because their chemistry points back toward a younger universe. Some of these stars may have formed in the early building blocks that later merged to create the Milky Way. Others may have been born in small dwarf galaxies and added to the halo when those systems were pulled apart. Their motions help reveal the difference. A star moving in a long tilted orbit, or even orbiting opposite to the disk's general rotation, may carry the signature of an outside origin. Its path is not random. It is a trace of the gravitational system it once belonged to, and the merger that brought it here. The halo contains many displaced witnesses, scattered through space in a way that only careful measurement can reconstruct. They are pieces of older galaxies still moving inside the Milky Way's pull. The word archaeology is not literal, but it fits the method. Instead of digging through soil, astronomers read positions, speeds, ages, and chemical fingerprints. A star's abundance pattern can show whether it formed in a region enriched slowly or rapidly, whether its parent cloud had received material from massive supernovae, or whether it belongs to a population unlike the main disk. When many stars are measured together, patterns emerge. Some group into streams. Some share chemical traits. Some reveal a past merger that is no longer visible as a separate galaxy. The halo, faint as it is, becomes a record of assembly. It shows that the Milky Way did not begin as the single graceful spiral now imagined from diagrams. It grew through smaller pieces, early collapses, gas inflow, star formation, and repeated absorption. Globular clusters deepen the same story. These compact spheres of stars orbit the Milky Way in the halo, often far above or below the disk. Each cluster can contain hundreds of thousands of stars packed into a dense, gravitationally bound swarm. Many globular clusters are among the oldest objects associated with the galaxy, with ages reaching back close to the early era of the Milky Way's formation. Their stars are usually metal-poor compared with younger disk stars, and their tight grouping allows astronomers to study ancient stellar populations in a concentrated way. They move around the galaxy like old lanterns, not attached to spiral arms, not involved in the ordinary star-forming life of the thin disk, but preserved in long orbits through the outer gravitational field. A globular cluster is not just a beautiful object. It is a surviving fragment of early galactic history, a dense pocket of stars that formed when the conditions of the universe were different. Their stability is part of their power. Open clusters in the disk often disperse over time, pulled apart by tidal forces, encounters with clouds, and the general motion of the galaxy. Globular clusters are far more tightly bound, and many have endured for billions of years. Inside them, stars live in crowded conditions that can produce unusual interactions. Some stars may exchange companions, Some may merge, some form blue stragglers, stars that appear younger and hotter than the surrounding population, likely created by mergers or mass transfer in close systems. Even in these ancient clusters, time has not been motionless. Their interiors have evolved dynamically while their overall identity has survived. They are ancient without being frozen. The halo also contains old stellar remnants, including white dwarfs that cooled for immense spans after their parent stars exhausted their fuel. A white dwarf is the dense core left behind by a lower mass star after it sheds its outer layers. It no longer produces energy through ordinary fusion, so it gradually fades as stored heat leaks into space. Very old white dwarfs in the halo can help measure the age of stellar populations, because their faintness records how long they have been cooling. They're quiet clocks, not as dramatic as supernova remnants or pulsars, but deeply informative. Some may have formed before the thin disk became the dominant bright structure of the Milky Way. The disk may carry the most visible light, but the halo carries the deeper time. Among the rarest halo objects are extremely metal-poor stars, sometimes with only a minute fraction of the iron found in the Sun. These stars are precious because they approach the chemical conditions left by the earlier stellar generations. They are not thought to be the very first stars themselves in most cases, because the first stars were likely massive and short-lived. Instead, they may be early generation survivors, formed from gas enriched by only one or a few previous supernovae. Their atmospheres can preserve the chemical imprint of those first explosions. In such stars, the Milky Way contains evidence not only of its own childhood, but of the universe's first attempts at making heavy elements. A faint red halo star can therefore carry a message from a time before the galaxy had spiral arms, before the Sun, before Earth, before even most of the elements that would later become planets were common. The halo's ancient stars also reveal what the galaxy has lost. Many of the small systems that contributed stars to the Milky Way no longer exist as intact galaxies. Their gas has been removed, their stars dispersed, their shapes erased by tides. What remains may be a stream, a cluster, or a population of stars whose orbits and chemistry still point back to a common origin. The halo is full of remnants of things that were once separate. Its emptiness is therefore deceptive. It is sparse, but not simple. It contains after-images of vanished galaxies, debris of old encounters, and survivors of conditions that no longer dominate the disk. The halo looks quiet because its stars are thinly spread and often faint. Its history is anything but quiet. It is the place where the Milky Way's growth can be read most clearly, precisely because the bright disk has not fully overwritten it. This changes the meaning of the Milky Way's age. The galaxy is not one object that formed all at once and then merely aged. Different parts record different times. The thin disk is active and comparatively young in much of its behaviour. The thick disk reaches further back. The bulge and bar preserve inner dynamical evolution. The halo extends into the oldest accessible memory, holding stars and clusters from the assembly era and from swallowed companions. A single galaxy can therefore contain many clocks. Some tick in star-forming clouds, some tick in cooling white dwarfs, some tick in chemical abundance patterns, some tick in the slow orbits of globular clusters. Together they show that the Milky Way is not only a place in space, but a layered time structure. Its present form is built on populations that remember older forms. The halo is the widest and dimmest of those memories, a region where the galaxy's beginning has not entirely dissolved. In the calm darkness around the disk, ancient stars continue their long paths, carrying traces of smaller galaxies, early clouds, and the first enrichments of matter. They do not explain the whole Milky Way by themselves, but they prevent the galaxy from appearing too young, too smooth, or too self-contained. They show that the bright spiral is the visible surface of a much older accumulation. The next step is to follow those traces from individual ancient stars into the streams they belong to, where the Milky Way's history of devoured galaxies becomes visible as long arcs of light around its halo. The Milky Way's halo is not only old, it is littered with the remains of things that used to be separate. Around the bright disk, long arcs of stars stretch through space in paths too thin and faint for the eye, but clear enough when their positions and motions are measured together. These arcs are stellar streams, the pulled-apart remnants of dwarf galaxies and star clusters that wandered too close to the Milky Way and began to lose their shape under its gravity. A small galaxy does not have to strike the disk directly to be destroyed. It only has to pass through the larger galaxy's gravitational field again and again, feeling a stronger pull on its near side than on its far side, until stars begin to peel away. Over time, the captured system is stretched into a ribbon. Its original body fades. Its stars continue along related orbits, marking the path of what once held them together. The stream becomes a ghostly diagram of disruption, a line of evidence drawn around the galaxy by gravity itself. This is one of the most revealing strange facts about the Milky Way. Its outer regions are full of broken companions, and the galaxy's present form is partly built from their loss. The process is slow enough to seem gentle from a distance, but it is still a kind of dismantling. A dwarf galaxy approaches with its own stars, gas, dark matter, and internal history. At first it may survive as a distinct satellite, orbiting in the Milky Way's halo while tides pull at its edges. Each close passage strips more material. Stars at the outskirts are least tightly held, so they escape first, drifting ahead of and behind the surviving core along the orbit. Gas can be removed by tides or by pressure from the Milky Way's hot halo, leaving the dwarf poorer and fainter. After enough passages, the original shape may be almost erased. What remains is a stream, sometimes wrapped around the Milky Way in a wide curve, sometimes plunging through the inner halo, sometimes spread so broadly that only careful surveys can recover the pattern. The galaxy does not swallow such companions in a single bite. It unravels them over immense time, strand by strand, until their stars become part of the larger system. The Sagittarius dwarf galaxy shows this process still underway. It is being disrupted as it orbits the Milky Way, shedding stars into a vast stream that traces great loops around the galaxy. Its remnants help map the Milky Way's gravitational field, because the path of a stream depends on the mass it moves through. If the dark matter halo were flatter, rounder, or lopsided, the stream would carry that influence in its track. Streams are therefore more than fossils of smaller galaxies. They are delicate traces of the invisible architecture surrounding the visible disk. By studying their curves, widths, speeds, and chemical patterns, astronomers learn both about the destroyed object and about the larger galaxy that destroyed it. The Milky Way's past mergers are not all as easy to see as Sagittarius. Some happened so long ago that the original companion has vanished completely. Its stars are now spread through the halo and thick disk, mixed with other populations but still recognizable through motion and chemistry. One of the most important ancient events is often called the Gaia-Enceladus merger, linked to a large dwarf galaxy that collided with the early Milky Way billions of years ago. Its stars move differently from those born in the main disk, many following stretched, plunging orbits that carry them through the inner halo. Chemically, they also show patterns that suggest a separate evolutionary history before the merger. This event may have helped shape the early halo and thicken the young disk, leaving a structural imprint that remains visible long after the incoming galaxy lost its name and boundaries. The Milky Way, in this view, is not a pristine spiral that merely grew by quiet accumulation. It is a composite, and one of its major components came from a collision large enough to reshape its youth. Retrograde stars make the same point in a different way. Most stars in the disk orbit the galactic centre in the same broad direction, following the rotation of the Milky Way's flattened body. But some stars, especially in the halo, move against that dominant flow. Their backward motion is difficult to explain if they formed calmly inside the rotating disk. It makes more sense if they arrive from smaller galaxies whose orbits were tilted or reversed before they were absorbed. A retrograde star is therefore not just a star travelling the wrong way. It is a moving clue, a fragment of an older orbit preserved inside a larger system. Tilted and elongated paths tell similar stories, when many such stars share related motions and chemical fingerprints. They can reveal the outline of a vanished dwarf galaxy more clearly than any photograph could. The object is gone, but its motion remains distributed through the Milky Way like a memory that has not fully dissolved. Chemistry is essential because motion alone can blur over time. As stars orbit through the galaxy, their paths can be stirred, stretched, and mixed. But a star's chemical composition is harder to erase. It carries the abundance pattern of the gas cloud in which the star formed. A smaller dwarf galaxy may enrich itself more slowly than the Milky Way, producing stars with different ratios of elements. Its supernova history, star formation rate, and gas loss all leave marks in its stellar population. When such a galaxy is absorbed, its stars do not become chemically rewritten. By combining chemical data with precise motion, astronomers practice a kind of galactic reconstruction. They group stars not by where they are now, but by where their history suggests they once belonged. This turns the halo into an archive of lost systems, each one faintly encoded in abundance and orbit. Stellar streams also show that the Milky Way is still growing. The galaxy has not finished collecting material. Small satellites continue to fall in. Some may survive for a long time. Others are already dissolving. Globular clusters can be stripped into thinner streams, their stars pulled away in leading and trailing tails. Dwarf galaxies leave broader trails because they contain more extended stellar populations and dark matter. Nearby companions are not simply ornaments around the Milky Way. They are active participants in its evolution, tugging, feeding, disturbing, and eventually losing material to the larger system. The idea of galactic cannibalism can sound harsh, but the physical reality is more patient and more complex. The Milky Way's gravity does not destroy every companion instantly. An absorption does not make the incoming stars meaningless. Once incorporated, they help build the halo, thicken the disk, seed streams, alter orbits, and enrich the galaxy's diversity of stellar populations. Some stars now counted as part of the Milky Way were born under other skies, in dwarf systems with different densities, chemical histories, and star formation rhythms. Their presence means the galaxy is not a closed family of native stars. It is a mosaic assembled from many environments. Even the Sun orbits within a structure partly shaped by ancient arrivals. Streams can also reveal small-scale structure that cannot be seen directly. If a stellar stream passes near a dense clump of dark matter, a massive molecular cloud, or another gravitational perturber, the stream may develop gaps, bends, or wiggles. These disturbances act like marks left on a quiet surface. In principle, they can help test whether dark matter is smooth or clumpy on small scales. The stars in a stream are so thinly spread that even a subtle gravitational encounter can leave a measurable signature. Their narrowness records the forces that have touched them. In this way, the ruins of dwarf galaxies may help answer questions not only about the Milky Way's history, but about the nature of the invisible matter that dominates its mass. Every stream carries two stories at once, the story of the object being torn apart and the story of the gravitational landscape through which its debris has travelled. The more streams are mapped, the less the Milky Way resembles a smooth, isolated disk. It becomes a record of arrivals, removals, and partial survivals. The halo is threaded with paths from systems that crossed the galaxy's boundary and never left in their original form. Some became long ribbons, some became diffuse populations, some may still retain small cores moving along their dissolving orbits. The bright spiral seen in diagrams is therefore only the visible face of a larger process of assembly. The Milky Way has grown by making stars from gas, but also by inheriting stars already made elsewhere. Its history is written in motion, and the writing is still being read. These streams lead naturally toward the unseen mass that shapes them. A dwarf galaxy can be pulled apart only because it moves through a gravitational field deeper than its own. A stream can map the halo only because the halo guides its orbit. A retrograde star can remain bound only because the Milky Way's mass reaches far beyond the bright disk. The story of devoured galaxies therefore points beyond starlight into the structure that holds the whole system together. The visible debris is delicate, but the force shaping it is immense and mostly hidden. Around the Milky Way, broken companions continue to trace paths through the dark, and their fading arcs begin to reveal the invisible architecture beneath the galaxy's luminous surface. The visible Milky Way is not massive enough to explain the way the Milky Way moves. That fact sits quietly beneath almost every modern map of the galaxy, because the stars, gas, dust, clusters, and glowing nebulae that can be detected directly do not provide enough gravity to account for the observed rotation of the disk. If the galaxy contained only what shines, absorbs, or emits, the outer regions should behave differently. Stars far from the centre should orbit more slowly, falling into a pattern more like planets around a star. Where distance weakens the central pull and orbital speed drops. Instead, the outer parts of the Milky Way move with unexpected speed. The rotation curve does not fall away as the visible mass suggests it should. Something unseen contributes gravity across the galaxy's outskirts, holding distant stars, gas, clusters, and streams inside a deeper field than the luminous disk can provide. This is the central clue that leads to dark matter. It is not introduced because the galaxy looks mysterious. It is introduced because the motions do not balance without it. The strange fact is not merely that the Milky Way contains invisible mass, but that the invisible mass appears to dominate the structure in which the visible galaxy is embedded. The bright spiral is only the lit inner layer of a larger gravitational body. Dark matter is a name for what is inferred, not yet a direct identification of what it is. It does not shine in telescopes. It does not block light like dust. It does not glow like hydrogen gas or reveal itself through ordinary emission. It is known by influence, by the way visible things move as if responding to mass that cannot be seen. In the Milky Way, that influence appears in the rotation of stars and gas, in the motions of satellite galaxies, in the paths of stellar streams, and in the way the galaxy holds together across distances larger than the bright disk alone can command. The dark matter halo surrounds the galaxy in a vast diffuse envelope. Unlike the thin disk, it is not flattened into the bright plane where the sun orbits. Unlike the spiral arms, it is not traced by blue stars and nebulae. It is a broad gravitational presence, extending far into the outskirts and likely containing most of the Milky Way's total mass. The halo is not visible as a glowing shell, yet its presence is written into the motions of everything that moves through it. This changes the meaning of the galaxy's size. The Milky Way cannot be defined only by where most stars are seen. Its true gravitational reach extends much farther into a region where stars are sparse. Globular clusters drift on wide orbits. Dwarf galaxies loop through the outer field, and streams from disrupted companions trace long paths through darkness. The bright disk may be the part most easily imagined, but the halo defines the galaxy's larger authority. A star at the edge of the disk does not respond only to the central bulge and the nearby spiral arms. It responds to the combined mass of the entire system, including a dark component spread through a halo far larger than the visible structure. In this sense, the Milky Way resembles an illuminated island inside a greater invisible terrain. The light marks where stars are concentrated. The gravity marks where the galaxy continues. Measuring that terrain is difficult because dark matter cannot be placed on a photograph. Astronomers estimate it by watching tracer stars in the halo, clusters far from the centre, satellite galaxies, streams, and gas motions. Each tracer gives a partial answer, and each comes with limitations. A satellite galaxy may have been disturbed by another companion. A stream may be affected by the shape of the halo. A distant star may have an orbit that is not yet fully known. The farther from the centre the measurement reaches, the harder it becomes to gather precise motion. This is why the total mass of the Milky Way remains uncertain. It is often described as being around 1 trillion times the mass of the Sun, but estimates vary because the outer halo is hard to weigh. The uncertainty is not a minor bookkeeping problem. The galaxy's mass affects predictions about the future encounter with Andromeda, the orbits of satellite galaxies, the survival of streams, and the boundary where the Milky Way's influence gives way to the wider local group. The home galaxy has a weight, but that weight is still being refined by the motion of distant objects. The rotation curve is the most famous clue, but it is not the only one. Dwarf galaxies orbiting the Milky Way move within the same extended gravitational field. Some of them are dominated by dark matter in their own right, containing relatively few stars but enough unseen mass to remain bound. Stellar streams, especially those stripped from globular clusters or dwarf galaxies, act as thin instruments laid through the halo. Their shapes can reveal whether the halo is round, flattened, stretched, or lumpy. If a stream has gaps or bends, those features may record encounters with massive objects, perhaps dark substructures that contain little or no starlight. This possibility matters because different ideas about dark matter predict different amounts of small-scale clumping. The Milky Way is therefore not only held by dark matter, it is also a laboratory for testing what dark matter may be like. The orbits of ruined galaxies become tools for examining a substance that has not yet been detected in ordinary form. The unseen halo also helps explain why the Milky Way could grow the way it did. In modern galaxy formation, dark matter gathers first into large gravitational wells, and ordinary matter falls into those wells, cooling into gas, forming stars, and settling into disks. The visible galaxy grows inside a dark scaffold. This does not mean dark matter builds stars directly. Ordinary matter still provides the gas, dust, chemistry, pressure, radiation, and cooling needed for star formation. But dark matter supplies the deep gravitational framework that allows matter to collect on galactic scales. Without that framework, the early universe would have had far more difficulty assembling galaxies like the Milky Way in the time available. The halo is therefore not an afterthought added to explain a modern rotation problem. It belongs to the entire history of the galaxy's formation, shaping the environment in which gas collapsed, smaller systems merged, and the disk eventually emerged. Yet the word halo can make dark matter sound smoother and simpler than it may be. A halo may have shape. It may be slightly flattened or stretched. It may be tilted relative to the disk. It may contain subhalos, smaller dark structures left from the merging of earlier systems. Some may host faint dwarf galaxies. Others may contain almost no stars at all. If these dark clumps exist in large numbers, they could disturb streams, influence gas, or help explain small irregularities in satellite motions. At the same time, observations place limits on how many such clumps can be present and how they behave. This tension is one reason the Milky Way is important. It is close enough that individual stars can be measured, streams can be mapped, and faint companions can be found. The galaxy's darkness is not inaccessible in the abstract. It presses on visible matter from every side, leaving traces that can be followed with enough patience. Still, dark matter remains unidentified. Many proposed particles have been searched for without a confirmed detection. Experiments underground, in space, and at particle accelerators have tried to catch some sign of interaction beyond gravity, but the answer has not yet settled. The Milky Way continues to behave as if the hidden mass is there, while the substance itself remains silent. That silence is scientifically productive rather than empty. It forces a distinction between evidence for mass and knowledge of material identity. The motions strongly indicate an unseen gravitational component. They do not yet reveal what that component is made of. The evidence is firm enough to shape galaxy models, but incomplete enough to leave one of physics' major questions open. In the Milky Way, that uncertainty is not far away. It surrounds the Sun, the disk, the halo stars, the satellite galaxies, and every stream moving through the outskirts. The galaxy's familiar light is moving inside a mystery that is not decorative, but structural. This hidden architecture gives a different meaning to the beauty of the spiral. The arms shine because stars form and die. The dust lanes darken because grains absorb visible light. The bulge glows with crowded old stars. The halo contains ancient clusters and faint streams. Yet all of these visible features occupy a gravitational frame whose largest component remains unseen. The Milky Way is therefore not simply a galaxy with a dark matter halo. It is a dark matter halo with a luminous galaxy settled inside it, bright enough to be seen from within, but not massive enough to explain itself. The next time the path inward turns toward the galactic centre, the same lesson remains, even where stars crowd together and the black hole waits behind dust. The visible drama is only part of the story. The galaxy's heart may be bright, dense, and restless, but it beats inside an invisible structure that extends far beyond the light. The centre of the Milky Way is hidden behind dust, but it is not still. From Earth, the direction of the galactic core lies towards Sagittarius, where the band of the Milky Way thickens into crowded brightness and then disappears behind dark clouds in visible light. The true centre cannot be seen directly by ordinary starlight, because the disk between Earth and the core is packed with dust grains that absorb and scatter the light trying to pass through. Yet other wavelengths pass more easily, and through infrared, radio, X-ray, and gamma-ray observations, the heart of the galaxy becomes less like a luminous blur and more like a layered environment of dense stars, hot gas, magnetic fields, compact remnants, and extreme gravity. At its centre lies Sagittarius, a star, the supermassive black hole around which the inner stars move. It is not large in the familiar sense of a glowing object spread across space. Its mass is enormous, more than 4 million times the mass of the Sun. But that mass is compressed into a region smaller than the scale of the inner solar system. It does not shine like a star. It reveals itself by what nearby matter does when gravity becomes too deep to ignore. The strongest evidence for Sagittarius A star comes from the motions of stars close to the galactic centre. These stars follow tight, fast orbits around something invisible. Over years and decades of observation, their positions trace long ellipses, some passing astonishingly close to the central mass before swinging away again. The orbits are too fast and too compact to be explained by an ordinary cluster of dark stars or remnants. The simplest explanation is a black hole, a region where gravity curves space so strongly that nothing crossing its event horizon can return. The stars do not fall in because most of them remain on stable paths, but their movement draws the outline of the unseen object. In this way, the black hole is mapped not by light coming from it, but by light coming from stars forced to move around it. The centre becomes visible through obedience. Every orbit is a sentence written by gravity. Sagittarius. A star is quiet today compared with the brilliant black holes at the centres of active galaxies. It is not feeding heavily. Only a small amount of gas and dust falls inward at any given time, and much of the material near it circulates, heats, or escapes rather than plunging directly across the event horizon. Still, quiet does not mean inactive. Flares sometimes rise from the region, likely caused by hot gas, magnetic activity, or clumps of material moving close to the black hole. In these moments, the centre brightens in infrared or X-rays, briefly revealing the energy of matter under extreme conditions. A black hole does not need to devour a galaxy to shape its surroundings. Even in a low feeding state, it governs the motions of nearby stars, influences the behaviour of gas, and marks the deepest gravitational point of the Milky Way. It is a sleeping engine, not a dead one. Around this engine, the inner galaxy is crowded and complex. Stars in the central regions orbit more rapidly than stars near the Sun because the mass density rises sharply inward. The core contains old stars, young massive stars, gas streams, stellar remnants, and magnetic structures tangled together in a space far denser than the local neighbourhood. Some stars there are difficult to explain because they are young and massive despite living near a black hole whose tidal forces should make ordinary star formation harder. Dense gas may have collapsed under unusual conditions, or stars may have migrated inward after forming elsewhere. The details remain under study, but the fact itself matters. The galactic centre is not merely an old graveyard of remnants. It also contains signs of recent formation, energetic motion, and material still being rearranged. The heart of the Milky Way is not simple age. It is age mixed with renewal under severe gravity. The central black hole sits inside the larger bar and bulge described by the galaxy's inner structure. The bar funnels gas inward over long periods, shaping the flow of matter through the central regions. Gas does not move toward the centre in a straight line. It follows elongated orbits, collides with other streams, loses energy, and gathers in rings and clouds. Some may eventually feed star formation. Some may drift closer to Sagittarius A star. Some may be expelled or heated before it can settle. This movement links the galaxy's large-scale shape to its smallest central scales. A bar tens of thousands of light-years across can influence whether material reaches the inner few light-years. The core is therefore not isolated from the disk. It is the receiving end of slow gravitational transport, where structures built over galactic scale gradually affect the flow of gas toward the deepest centre. Above and below that centre rise the Fermi bubbles, two enormous lobes of gamma-ray emission, extending tens of thousands of light-years from the galactic plane. They're invisible to human eyes, but in high-energy light they form one of the Milky Way's most striking hidden structures. Their origin is still debated. They may be the remains of a past outburst from Sagittarius, a star, when the black hole fed more actively and launched energy outward. They may also be connected to intense star formation near the centre, where many massive stars and supernovae drove hot gas into the halo. The evidence does not yet force one explanation completely. What the bubbles do show is that the Milky Way's core has not always been as subdued as it appears now. At some point in the relatively recent geological or astronomical past, the centre released enough energy to leave vast lobes above and below the disk. the galaxy carries an echo of central activity, suspended far beyond the region where it began. This possible past activity changes the emotional shape of the core. The Milky Way is often imagined as a calm spiral, mature and moderate, unlike the blazing active galaxies whose centres shine across the universe. But our own galaxy may have had episodes when the central black hole or central star formation was far more energetic. It may never have been a quasar in the most extreme sense known from distant galaxies, or at least there is no settled need to describe it that way with certainty. Yet it could have flared, brightened, and driven material outward. Light from past outbursts may have illuminated surrounding gas clouds, leaving delayed traces as radiation echoes. The centre seen now is only the current state. A black hole can sleep for long intervals and then awaken when gas reaches it. Galactic centres are not defined only by what they're doing at the moment of observation. They are defined by cycles of feeding, quieting, and response. The core is also a place where ordinary stellar systems can be broken apart. Binary stars passing too close to Sagittarius. A star may be separated by tidal forces. One star can be captured into a tighter orbit while the other is flung outward at extreme speed, becoming a hypervelocity star that may eventually escape the galaxy. Gas clouds can be stretched into long streams. Dust can be heated until it glows at wavelengths invisible to the eye. Magnetic fields can become twisted by the motion of plasma. Near the centre, gravity does not merely hold objects in orbit, it edits systems, rearranges partnerships, and converts close passages into lasting consequences. The violence is usually not seen as a sudden flash from Earth. It is inferred from trajectories, emissions, and rare objects moving far too fast for ordinary disk history. The core leaves evidence in things it sends away. Yet the galactic centre is not chaos without structure. It has patterns, rings, streams, orbiting star clusters, and repeated physical processes. Extreme environments can be orderly in their own way. The stars near Sagittarius. A star follow predictable paths. Gas responds to gravity, pressure, and magnetic fields. Radiation rises from known mechanisms, even when details remain difficult. The mystery lies not in the absence of rules, but in how many rules operate at once under conditions hard to observe directly. Dust blocks visible sight, crowding blends stars together. Timescales vary from minutes for flares to millions of years for larger gas flows. The centre has to be studied as an environment where many layers overlap, each requiring a different instrument and a different patience. The Milky Way's heart is therefore not a single object. Even though the black hole anchors it, it is a region where the galaxies bar, bulge, gas, stars, remnants, magnetic fields, and past eruptions all converge. Sagittarius. A star is the deepest point, but the core's meaning comes from the surrounding system as well. It is hidden from ordinary view, quiet by the standards of active galaxies, and still capable of shaping enormous structures above and below the disk. It can hold stars in rapid orbits, tear apart binaries, flare in high-energy light, and preserve traces of older outbursts. The calm band of the Milky Way overhead gives little hint of this interior. Behind the dust, the galaxy's centre is crowded, layered, and watchful, a sleeping engine surround. Some objects in the Milky Way do not behave like settled residents of a spiral disk. They cross the galaxy on steep paths, pulse with impossible regularity, drift without a parent star, or leave the galaxy entirely. After the crowded centre, these wanderers show what happens when gravity does more than hold a system together. It can also accelerate, scatter, unbind, and send pieces of the galaxy outward into lonelier regions. Hypervelocity stars are among the clearest examples. Most stars remain bound to the Milky Way. following orbits shaped by the combined pull of the disk, bulge, halo, and dark matter. A hypervelocity star is different. It moves so quickly that it may escape the galaxy's gravity altogether, passing from the stellar city into intergalactic space. One route to such speed begins near the central black hole. If a binary star system passes too close to Sagittarius A star, the black hole's tidal force can break the pair apart. One star may be captured onto a tighter orbit, while the other receives a tremendous gravitational kick and is thrown away. The event is silent across ordinary distance, but the result is unmistakable: a star travelling alone at speeds far beyond the usual motion of the disk. It carries with it evidence of a past encounter with the deepest gravity in the galaxy. Not every fast star comes from the central black hole. Some may be accelerated when one member of a binary system explodes as a supernova, removing mass and flinging the companion away. Others may be ejected from dense star clusters through close gravitational encounters involving several stars. The details differ, but the theme is the same. A star that seems solitary may have begun inside a partnership or cluster, and its present loneliness may be the outcome of an earlier disruption. The Milky Way contains many such displaced objects, stars whose paths no longer resemble the calm rotation of the thin disk. Some race across the halo, some dive through the plane, some are old arrivals from swallowed dwarf galaxies, others are young runaways from recent stellar violence. Motion becomes biography. A star's speed and direction can reveal the event that changed its life more clearly than its light alone. Rogue planets carry the wandering theme into deeper darkness. A planet is usually imagined as part of a system, orbiting a star, receiving light, and sharing a gravitational order with other worlds. But planets can be lost. Young planetary systems are crowded and unstable, and gravitational interactions between forming planets can eject one world into space. A close stellar encounter can strip planets from their stars. Some objects may even form in isolation from collapsing gas clouds, resembling planets in mass but lacking a true stellar parent. Once free, a rogue planet drifts through the galaxy with no sunrise, no familiar year, and no central flame. Detecting such bodies is difficult because they are dim. Some can be found through microlensing, when their gravity briefly magnifies the light of a background star. Others may glow faintly in infrared if they are young and still warm from formation. Their numbers remain uncertain, but the possibility that the Milky Way may contain vast populations of unbound worlds changes the picture of what a galaxy contains. It is not only stars and the planets attached to them, it may also be filled with dark planetary bodies moving independently through the spaces between. Some rogue planets may keep internal heat for long periods. A thick atmosphere, radioactive decay, tidal history before ejection, or residual warmth from formation could allow certain worlds to remain warmer than expected, at least beneath their surfaces or under insulating layers. This does not mean they are comfortable places, or that life is likely on them. It means that the absence of a star does not reduce every world to a single simple state. The galaxy may contain planets that no telescope can see directly, carrying frozen surfaces, hidden oceans, dense atmospheres, or rocky interiors through the dark. They are not part of the familiar bright architecture of spiral arms, but they still belong to the Milky Way's population of travellers. Their presence suggests that the galaxy's unseen inventory is richer than starlight implies. Pulsars are different kinds of messengers. They are not quiet wanderers, but compact remnants left after massive stars collapse into neutron stars. A neutron star packs more mass than the Sun into a sphere only the size of a city, producing matter so dense that ordinary comparisons fail. If the remnant spins and its magnetic poles send beams of radiation into space, Those beams may sweep past Earth like the light from a cosmic lighthouse. Each sweep appears as a pulse. Some pulsars rotate slowly by stellar standards, while others spin hundreds of times each second with astonishing precision. Their regularity makes them useful as cosmic clocks. By measuring tiny changes in pulse timing, astronomers can study the interstellar medium, test gravity, find planets around dead stars, and search for long-wavelength gravitational waves using networks of pulsars spread across the galaxy. A pulsar is the remnant of catastrophe, but it becomes an instrument of order. Pulsars also show how the Milky Way preserves stellar death in active form. A supernova may fade, but the neutron star left behind can keep broadcasting for millions of years. Its beam crosses space, delayed and distorted by electrons between the stars. Its timing can reveal whether it is moving through a binary system, whether it is slowing with age, or whether space-time itself has been stretched slightly by passing gravitational waves. Some pulsars are kicked at birth, launched by asymmetries in the supernova that created them. They travel through the galaxy as high-speed remnants, leaving trails or bow shocks in surrounding gas. Like hypervelocity stars, they show that stellar death can produce motion as well as debris. Like clocks, they make that motion measurable. The galaxy's strangest travellers are not always large objects. Cosmic rays pass through the Milky Way as high-energy particles, mostly protons and atomic nuclei, accelerated by supernova remnants, pulsars, stellar winds, and perhaps more extreme sources. They move close to the speed of light, but they do not travel in simple straight lines. Magnetic fields bend their paths, scattering them through the disk and halo until their origins become difficult to trace. When cosmic rays strike gas in space, they can produce gamma rays. When they reach Earth's atmosphere, they trigger cascades of secondary particles. They are small compared with stars, but they carry enormous energy for their size and influence the ionization and chemistry of interstellar clouds. The Milky Way is not only filled with matter moving under gravity, it is threaded by charged particles guided by magnetism, an invisible weather that carries information from violent events across great distances. Neutrinos are even more elusive. They are produced in nuclear reactions in stars, in supernovae, and in high-energy processes throughout the universe. They pass through ordinary matter almost without interaction, crossing planets, stars, and the galaxy itself as if almost nothing were there. Most cannot be traced to particular Milky Way sources, but supernova neutrinos would provide a direct message from the collapsing core of a dying star if one occurred nearby. Unlike light, which may be delayed or hidden by dense material, neutrinos can escape from deep interiors almost immediately. They are ghostly, not because they are imaginary, but because they barely touch the matter they pass through. In a galaxy full of dust, gas, and magnetic fields, neutrinos move with a kind of severe independence. They carry news from places light struggles to leave: white dwarfs, neutron stars, black holes in binary systems, and wandering remnants add still more motion to the hidden traffic of the Milky Way. A white dwarf can drift for billions of years as it cools. A black hole left by a massive star may move invisibly unless it feeds from a companion or bends the light of a background star. Binary systems can exchange mass, ignite outbursts, or merge. Some compact pairs radiate gravitational waves as their orbits shrink. The galaxy is full of these small, intense systems, many of them faint, dark, or intermittent. They are not decorative exceptions. They are part of the natural outcome of stellar evolution in a galaxy old enough to have produced many generations of stars. For every bright young star in a nursery, there are older remnants travelling through the disk or halo, marking the aftermath of earlier light. Together, the wanderers make the Milky Way less like a static spiral and more like a vast exchange of departures. Stars can be flung from clusters, planets can be separated from stars, pulsars can tick across the disk after violent births, cosmic rays can scatter through magnetic fields, neutrinos can cross almost everything without slowing. Some travellers remain bound, some may leave forever, some are visible only by timing, gravity, or rare interactions. They show that the galaxy is held together by gravity, but not every object remains comfortably nested in place. The same forces that assemble the Milky Way also create escape routes, solitary paths, and messages that move through the dark long after their sources have changed. The galaxy's motion is therefore not only the smooth rotation of a disk, it is also the sudden ejection, the patient drift, the pulse, the particle, and the remnant crossing a structure too large for any single path to define. The Milky Way is not alone in the dark. Beyond its warped disk, beyond its halo of old stars and invisible mass, smaller galaxies move under the same wide gravity, some close enough to feel the Milky Way pulling at their gas and stars, others drifting farther out in the shared field of the local group. This collection is not a crowded cluster like the great galaxy cities found elsewhere in the universe. It is a loose family spread across millions of light years, dominated by two large spirals, the Milky Way and Andromeda, with Triangulum and many dwarf galaxies scattered around them. Some dwarfs are bright enough to have names and shapes. Others are so faint that they contain only sparse stars embedded in dark matter, barely distinguishable from the background except through careful surveys. The local group looks calm because its members are separated by enormous distances, yet calm is not the same as stillness. The galaxies are gravitationally bound. They curve around one another, fall inward, orbit, disturb, and slowly gather. The Milky Way is therefore not a solitary island. It is one of the main masses in an archipelago of galaxies, and the future of that archipelago is being written by motion. The nearest companions are the dwarf galaxies that orbit or pass near the Milky Way. Some are ancient satellites, though even that word can hide uncertainty. The large and small Magellanic Clouds are the most visible examples from Earth's southern skies. Two irregular dwarf galaxies bright enough to be seen without a telescope. They contain gas, young stars, star-forming regions, and their own disturbed histories. For a long time, they were often described as long-term companions circling the Milky Way. More recent motion measurements suggest a more complicated possibility they may be on their first close approach, or at least relatively recent arrivals in the Milky Way's immediate neighbourhood. Their speeds are high, and their interaction with the Milky Way's halo is still unfolding. If they are newcomers, then the galaxy is not only preserving ancient mergers from deep time, it is also responding now to fresh arrivals, large enough to tug at the outer disk, disturb the halo, and leave long trails behind them. The Magellanic Stream makes that disturbance visible in radio light. It is a vast ribbon of hydrogen gas trailing from the Magellanic Clouds across a large arc of the sky, invisible to ordinary eyes but traced through radio emission. This gas has likely been stripped by tidal interactions between the clouds themselves and by the Milky Way's gravitational influence, with pressure from the hot halo also playing a role. The stream is a record of motion and loss. It shows that satellite galaxies do not simply orbit like clean points around a central body. They carry gas that can be pulled away, stretched, heated, and eventually folded into the larger system. Some of this material may one day fall into the Milky Way and help feed future star formation. Some may remain suspended in the halo. In either case, the stream reveals the local group future in miniature galaxies exchange matter before they fully merge, and their outskirts begin to mingle long before their stars settle into one system. Other satellites tell quieter versions of the same story. dwarf spheroidal galaxies around the Milky Way are faint, old, and often poor in gas, suggesting that their ability to form new stars has been reduced or ended. Their stars preserve chemical and orbital records of small galactic lives shaped under the shadow of a larger neighbour. The Milky Way is surrounded by companions in different states of survival, some intact, some stretched, some nearly erased. Around Andromeda, a similar retinue of dwarf galaxies moves in its own gravitational field. The local group is therefore not a collection of finished objects, but a set of relationships, each one changing the others in ways that become visible over immense time. The largest relationship is between the Milky Way and Andromeda. Andromeda lies more than 2 million light-years away, yet it is approaching rather than receding, on cosmic scales, where the expansion of the universe carries distant galaxies away from one another. This local inward motion is possible because the local group is gravitationally bound. The mutual pull of the Milky Way, Andromeda, their dark matter halos, and surrounding matter is strong enough to overcome expansion within this neighbourhood. Andromeda is not falling straight toward the Milky Way like a stone dropped from above. Its exact sideways motion matters, and that motion determines how the galaxies will first pass, distort, and eventually merge. Current models indicate that in roughly 4.5 billion years, the two great spirals will begin a long encounter. The phrase collision can make the event sound like stars smashing into stars, but that is not what galactic collisions usually mean. Stars are so small compared with the distances between them that direct stellar impacts will be extremely rare. The real collision is gravitational. Dark matter halos will overlap. Gas clouds will be compressed or stripped. Stellar orbits will be reshaped. Spiral arms will stretch into tidal tails. The neat disks of both galaxies will be distorted by the encounter, pulled into arcs, loops, shells, and streams before the systems settle. If gas remains abundant enough, bursts of star formation may ignite where clouds are driven together. The central black holes of the Milky Way and Andromeda may eventually sink toward the common centre, losing orbital energy through interactions with stars and gas before forming a bound pair. Their final merger, if it occurs after a long inward spiral, would release gravitational waves across billions of years. The two spirals may become one larger galaxy, though the final form depends on gas, orbital details, and the participation of Triangulum and other companions. For Earth, if it still exists as a recognizable planet at that time, the night sky would change long before the final merger. Andromeda would grow larger in the sky as it approached. Its disk would become brighter and more structured. Later, as the galaxies interacted, the sky could contain warped bands, tidal arcs, and intense star-forming regions. Yet the solar system itself might pass through the encounter without any close stellar collision. Its orbit around the new combined system would likely be changed, perhaps moved outward, or placed on a more elongated path, but not necessarily destroyed by the galactic merger itself. The greater threat to Earth's surface conditions comes from the Sun's own evolution across similar timescales, not from stars physically crashing into the planet. Galaxies can merge while most stars continue moving through open space, their paths rewritten by gravity rather than by impact. The local group future also includes smaller acts of absorption. The Magellanic Clouds may eventually merge with the Milky Way, bringing their stars, gas, and dark matter into the larger halo and disk. Other dwarf galaxies may be torn apart into streams. Some satellites may survive for long periods, especially if their orbits keep them distant. Triangulum may interact with Andromeda, the Milky Way, or the eventual merge system in ways that remain sensitive to its present motion. Over time, the local group may become less like a set of separated galaxies and more like one dominant remnant with a halo of faint companions. This process is not unusual. Galaxy growth through mergers is a central part of cosmic history. What makes it feel strange is that the Milky Way is involved. The same galaxy that holds the Sun in a quiet spur is also part of a larger gravitational future, one in which its identity as a separate spiral is temporary. Even the local group itself exists within a larger environment. It lies near other galaxy groups and the broader cosmic web, though it is not bound to every structure around it. On the larger scales, the expansion of the universe continues. Distant galaxies beyond the local group will recede, and over very long times. Many will move beyond reach of observation from any future inhabitants of the merged remnant. Local gravity gathers nearby systems while cosmic expansion carries distant systems away. The Milky Way's future therefore has a double character. Nearby, galaxies fall together. Far away, the universe opens outward. That contrast gives the coming merger its quiet weight. It is not an isolated spectacle, but the natural consequence of gravity acting inside a bound neighbourhood. The Milky Way has grown through past mergers, is being disturbed by present companions, and will be transformed by future ones. Its spiral shape is not permanent, nor is Andromeda's. The local group is a slow gathering, a set of islands whose distances are vast but not enough to prevent eventual change. In that gathering, the galaxy's future begins to resemble its past. Smaller systems are absorbed, streams are drawn out, gases exchanged, orbits are rewritten. The difference is scale. The next great encounter involves another major spiral, a galaxy large enough to remake the architecture of both. For now, the Milky Way remains itself, a barred spiral with a hidden core, a dark halo, and a moving family of satellites. But the future moves toward it through Andromeda, gently, steadily, and without hurry. The galaxy called home is not an endpoint in the local group. It is a chapter in a longer gravitational assembly, and that unfinished state leads back to the present Milky Way, still drawing in gas, shaping fields, forming stars more slowly, and becoming something new even before the distant merger arrives. The Milky Way is old, but it is not finished. Its spiral arms have shifted across time. Its halo has gathered the remains of smaller galaxies. Its central black hole has passed through quieter and more active phases, and its disk continues to receive, lose, cool, heat, and rearrange matter. A galaxy can appear timeless because its changes unfold more slowly than any ordinary witness can follow. Yet the evidence points to constant transformation. Gas still moves through the halo and into the disk. Stars still form inside cold clouds. Stellar winds and supernovae still push material outward. Magnetic fields still thread the interstellar medium, guiding charged particles and shaping the behavior of dust and plasma. The Milky Way is not a completed object suspended in space. It is an evolving system, still becoming itself through the same processes that built it. The strange fact is that home is not a settled place, even at galactic scale. It is a structure in motion, held together by gravity, stirred by death and birth, and slowly altered by matter arriving from beyond its visible edge. Some of that arriving matter comes as gas from the wider cosmic environment. The galaxy does not exist as a closed vessel. Around it stretches a halo of hot, faint gas, dark matter, old stars, streams, and satellite systems, all connected in subtle ways to the larger cosmic web. Fresh gas can fall inward from intergalactic space or from the stripped material of smaller galaxies. Some arrives warm or hot, difficult to cool quickly. Some may condense into clouds that drift toward the disk. Some is recycled gas that once left the disk through supernova-driven outflows and later returned in a galactic fountain. This circulation matters because star formation consumes cold gas. Without some replenishment, a galaxy eventually exhausts the material from which new stars can form. The Milky Way's present rate of starbirth is slower than it was in younger eras. But it has not stopped. The galaxy is in a mature phase, not an extinguished one. It still has reserves, inflows, and cycles that allow new stars to appear in scattered nurseries across the disk. This slower pace gives the Milky Way a calm quality compared with more violently active galaxies. It is not producing stars in a great starburst. It is not blazing as a quasar. Its central black hole is quiet by cosmic standards, and its disk forms stars at a measured rate. But calm should not be mistaken for simplicity. Beneath the steady appearance, gas is constantly changing state. Cold clouds collapse in one region, while hot bubbles expand in another. Dusk grains align with magnetic fields. Cosmic rays move through tangled paths. Shock waves from dying stars cross the interstellar medium. The halo stores material that may later fall back. Satellite galaxies lose gas that may one day join the larger system. These movements are not dramatic when seen in a human lifetime, but they are the galaxy's metabolism. The Milky Way continues by cycling matter between forms, temperatures, locations, and generations. Magnetic fields add an invisible order to this circulation. They are weak compared with magnets on Earth, but across light years they become important. The galaxy's magnetic field threads through the disk and reaches into the halo, affecting how charged particles travel and how gas responds to pressure and turbulence. Dust grains can align with these fields, polarizing starlight and leaving clues that radio and microwave observations can decode. Cosmic rays do not simply fly straight from their sources. They are bent, scattered, and delayed by magnetic structure. In cold clouds, magnetic support can slow collapse, helping determine whether gas becomes a star quickly, waits, or disperses. The Milky Way therefore has architecture that cannot be seen in visible light, and cannot be reduced to gravity alone. It glows, turns, and gathers under gravity. But it also hums with magnetism, an unseen pattern influencing the space between stars. Dust, often treated as an obstacle, is part of this unfinished story as well. It blocks visible starlight and hides the centre, but it also carries chemistry across the galaxy. In cold interstellar clouds, atoms and molecules settle onto grain surfaces, where reactions can occur in ways that empty space would not easily allow. Water ice, carbon-rich molecules, and other organic compounds can form or accumulate in these environments. Organic does not mean living. It means carbon-based chemistry, the kind of chemistry that can later become important in planets, comets, and prebiotic environments. When a molecular cloud collapses, this material can be incorporated into disks around young stars. In those disks, dust grains collide, stick, grow, and become the first solid steps toward planets. The chemistry of a future world may begin long before the world itself exists. Inside a cold cloud that once drifted unnoticed through a spiral arm. This gives the Milky Way a quiet biological relevance without claiming more than the evidence allows. The galaxy is not known to be full of life. No confirmed life has been found beyond Earth. Yet the ingredients associated with planetary systems and organic chemistry are not isolated to one rare corner. Planets are common around stars. Dust and gas contain carbon compounds. Water appears in many cosmic environments. Heavy elements, made by earlier stellar generations, are widely distributed through the disk. These facts do not make life inevitable, but they make the galaxy chemically generous. Earth is one example of that generosity carried to complexity. a planet formed from recycled matter around a stable star in a relatively quiet region of the disk. The same galaxy that holds black holes, supernovae, rogue worlds, and dark matter also carries the raw ingredients from which habitable environments may arise. Its strangeness and its gentleness are not opposites. They belong to the same system. At the same time, the Milky Way's future is limited by time and fuel. Star formation will continue only as long as enough cold gas can gather into dense clouds. Over the long future, gas will be consumed, heated, expelled, locked into long-lived stars, or stirred into forms less able to collapse. The merger with Andromeda may reshape the galaxy, and perhaps trigger new waves of star formation if gas remains available. But even that future activity will not last forever. In the deep future, the combined remnant will likely become redder, quieter, and poorer in young blue stars. The present Milky Way therefore occupies an intermediate chapter. It is not young and turbulent in the way early galaxies often were. It is not yet a faded stellar remnant. It is a mature spiral still rich enough to build new systems, old enough to contain ancient fossils, and massive enough to keep drawing smaller structures into its story. The galaxy's unfinished nature is visible in its irregularities. A perfect spiral would suggest a system untouched by disturbance, but the Milky Way is warped, lopsided, barred, layered, and surrounded by streams. These are not defects. They are signatures of history still acting in the present. The Magellanic clouds tug at the outer regions. Stellar streams continue to wrap through the halo. The dark matter halo guides motions that remain only partly mapped. Gas fountains rise and fall. The bar shapes the inner disk. The central black hole waits in its quiet phase. Each piece belongs to a different time scale, and together they prevent the galaxy from becoming a static emblem. The Milky Way is a record of change that has not ended. It carries the ancient universe in its metal-poor stars, the present cycle in its nurseries and dying stars, and the future in its incoming gas and approaching companions. From the position of Earth, this vast becoming is mostly silent. The night sky gives no obvious sign that the sun is moving around the centre, that dark matter surrounds the disk, that magnetic fields thread the space between stars, or that ancient streams arc through the halo. The galaxy's activity is hidden by scale, distance, dust, and slowness. Yet the hidden processes are not separate from the small planet that observes them. The atoms in Earth were shaped by the galaxy's recycling. The sun formed from a molecular cloud enriched by older stars. The solar system travels through the disk as the Milky Way turns. Life on Earth developed inside one moving pocket of a much larger structure, neither central nor detached, but included. That inclusion is the final strange fact behind all the others. The Milky Way is not only an object overhead, it is the environment from which the solar system emerged and through which it continues to move. Its invisible mass holds the orbit. Its old stars preserve the beginning, its dust hides nurseries, its dying stars supply elements, its future merger waits far beyond the human present. The galaxy remains unfinished, but not empty of meaning. It is a slowly changing home, bright in fragments, dark in structure, ancient in memory, and still quietly forming what will come next. The galaxy remains in motion after the narration grows quiet. Stars continue their long arcs around the hidden centre. Cold clouds drift through the spiral pattern, some waiting in darkness, some beginning the slow inward fall that will one day become light. In the halo, ancient clusters keep their patient orbits, holding the memory of an earlier universe in stars that burn faintly and steadily. Far above and below the disk, old streams from vanished galaxies continue to trace the paths of encounters, almost erased by time. Nothing in the Milky Way is truly motionless. yet almost all of its movement is gentle to human senses, stretched across spans too wide to feel. That is part of its quiet power. The galaxy can be familiar as the pale band of night and still remain almost immeasurably strange. It can be home and mystery at once. The sun keeps travelling through its minor spur, carrying Earth through the dark with no need for awareness or effort. Around it, the galaxy holds the remains of dead stars, the beginnings of future systems, the unseen weight of dark matter, the soft chemistry of dust, and the distant approach of Andromeda. Every part belongs to a larger unfolding, not hurried, not finished, and not fully revealed. In that slow turning, the Milky Way becomes less like a fixed object and more like a long, luminous process. It gathers, scatters, hides, reveals, and begins again. The quietest truth is that this vast structure is not separate from the small world that wonders about it. Earth is made from its older fires, sheltered within its motion, and carried inside its unfinished story. The galaxy turns on, ancient and patient, while its stars keep crossing the dark,